So we'll continue with the project demonstrations. First of all, I'll be talking about UAD PARROT, followed by my colleague Tiong with Kinect sensor, and then Choreography of TurtleBot by Seng, and lastly, Kelvin will be talking about LIDAR sensor. So I'll begin with the UAD quadruples. So basically what I've done in this past few weeks is that I first make the compilation for the SDK file, which is the software development kit, and then I proceed with to compile the driver, which is based on the official SDK that AR-Drone 2.0 PARROT released. And I've tried a few drivers, which is first of all was Brown AR-Drone, which is a simplified version of the whole package. So, I mean, the person actually it takes a few parts of the entire SDK file to make a smaller file for it to run some basic executions. And secondly, I proceed with the AR-Drone autonomy with RAF, that is compiled based on Cat-King. And lastly, I tried, I managed to do it based on Rose build as well. So once these packages are done, I tried out with I list out the topics and look into what is in it. So as you can see, there are close to like 30 topics over here, which justify the complexity and the stability of the drone PARROT. And there are the bottom cameras, front cameras, and the IMU, the inertial measurement unit, and the landing node navigation data, reset, trigger for emergency, command velocity, and all of it. So, and within the navigation data itself, there are a whole bunch of the details here. As you can see, the headers and have the timestamp, the magnetometer for X, Y, and Z direction. And it takes into consideration for the wind speed and wind direction in order to counter it to hover on one location. And it goes on with the rotation in X direction, Y direction, and Z direction, the velocity, acceleration, and all the motor speeds. And in this part, as you can see, is the text recognition, which I will be showing a video later. So once these are done, I started off with some basic commands lines teleoperation, and I've compiled a video here. So a few things I need to do. You roll score it, and then you run the AR-Drone package for the AR-Drone driver. So of course, all these are done after the Wi-Fi connection is established, and then this is the topic that we published to the reset button that triggers the emergency lights. So as you can see, this is in red. And after I send the command again, it changed into green color, and that will mean that the drone is ready to fly. And this is for the image view. We look into the cameras of the drone over here. And this is the TurtleBot in front of it, and this is the image that we have. So although it looks like a picture, it's true, right? So I'll keep the video and let it fly so that you can see the moving image. So this is we publish the signal to the taking off node. So yeah, so we did, and then we try on the landing as well. The landing. So on this part is still quite stable, although it's on the tablet because of this little the tabs, so it can actually capture the image so that it knows its location to hover on the same location. But then later in other videos, you can see it's like quite moving around because it's not directly on top of the what do you call this orange tape. Yeah. So once the command lines are okay, I proceed with keyboard teleoperation, which is more intuitive. So again, we try out with once we cross launch the the commands, and we'll try out with the emergency toggle button first. So it's originally in green, and once I press the space bar, since it's the biggest, and it changes into red and green like that. It's red and then green. So as you can see, this is the camera view over here. And once I focus on this window, and these are the buttons for moving it front, back, left, right, and the rotation in that direction. And then landing button. So that is for keyboard operation, and I'll proceed with joystick after that. And in this part, I have included this tag recognition over here, as you can see. Again, we begin with the emergency toggle button first, which I set it on the blue button over there. So it turns red, and then green, red, again, press again, and green. And the landing, I set it as the start button. It moves up. As you can see, it's not quite stable this time around. So rotation, and then the movement. The movement will be on the right joystick, and these are for the altitude as well as the rotation in Z direction. So, and then I zoom in into the camera view over here. So what it does is it's actually showing a green dot on the target. So you focus on the color tape over there, and then display the distance. As you can see now, it's close to 2.7, and then as you move further, it actually shows greater magnitude and smaller magnitude. So since the AR drone is moving around, as you can see, the target is always identified, and the distance is displayed. Okay. So once these are done, I proceed with camera-based navigation, which is based on PCAM, which is parent tracking and mapping. So as you can see, this is the map almost generated, okay? And these are the image view. And once we toggle the spacebar button, it will start to recognize its initial location. So these are the key points identified. I mean the one in red color. And since the parrot is not quite stable, as it's moved, it will show a line. I mean from the original location of the dot. So and what we have here is the graphical user interface, and there are 4 choices: joystick, keyboard, autopilot, and nothing. So I was doing an experiment based on the autopilot, and what it does supposedly is it takes off, and then it should start taking its original location, and then it goes up a little bit to take the stereo in to determine the distance, since it has only one camera, so it needs 2 locations in order to know the distance. And what it does is normally it takes off, and then it goes up and down for close to 1 meter. And these command lines, this programming is another form of language that is determined by master students based on his master thesis. And this is the original position of the drone, and then it can go to different coordinates. And this X, Y, Z, and this last digit here will be the angle for the Z direction rotation. And yeah, so basically I'm still quite new to this, since I spent the last week on focusing on make it work on the laptop instead of my workstation. So and some further recommendations, since it's not during the experiment, the drone actually suddenly loses control and goes quite high, and it hit the ceiling, and it toggled the emergency button to stop all the propeller, and it just dropped from like close to 10 feet. and then the center cross was broken. And I looked into the design of it. It's not quite built to last, since although these screws are as mentioned is made by the quite robust materials and carbon fiber, all this. But the center of it, this one, is made of plastic. But then in this one, for what I show here, these are all aluminum, so I believe it will be more robust. And in a case that we might prefer to use the original, in case that it might affect the navigation, the stability, if we are using the original central cross, it will be good if we can use a zip tie as cushion. These are the normal zip tie that we use to tie things, and it can only go one way. So this will actually provide some suspension as it lands. So according to some videos I've seen on the internet, it can actually go up for 30 feet, about 10 meters, and it drop on glass, it's still okay. Just that this thing will break, but other things are functioning. So these are like, I don't know, just a few, less than €1. Okay. As for batteries, actually we expected the battery to last for about 1 hour, but 1 hour is just for it to stay on and get ready. When it starts flying, one battery can only last for close to 10 minutes, and I finished all the 4 batteries within 40 minutes. So it will be good if we can use the extended battery life, which is 150 mAh, but the one that we have is only 1000. So it will extend the period for the experiment. And of course, as we conduct the experiment, since we only start with the garage, as well as one AR drone, it will be good if we can have a lot of accessories, since it will eventually wear out and get spoiled during the experiments. So I think this will be necessary in the future. And like the center cross has broken, and probably the next will be the motor or maybe the camera or this. One thing I found with the camera is that this camera that they are selling, instead of only one position, it can actually goes up and down, so it will be good for like maybe civilians, for the camera, for the maybe image reconstruction, all this. So proceed with teamwork maybe. Since I'm quite alone in the project, what I show you here, this picture, are the team that actually managed to bring the quadrupeds up to TED. Consists of like 7 professionals working full-time on it, and I believe with a pretty strong teamwork, they can actually excel and go further, instead of just get nose to some little things. And to make a huge impact, we really need the teamwork to go on. And frankly speaking, I'm not going to stop after the internship here in August. I'll continue afterwards. So it'll be great if the projects carry on, and then I'll be working maybe in Malaysia to continue the research with people in LE2I. So these are the future work that I'm going to work on. First of all will be the target tracking, the one that we have seen previously, that maybe a box, or we just use the tag that is produced by the company itself to just paste on maybe something, since it can be recognized, and then to design a control loop for it to keep for distance, certain speeds, to follow the direction or the location of the box itself. And then I'll go on, hopefully I'll go on, since the time is really packed, hopefully this can be done within like 2 weeks time. And then I'll go on with some real life application, if I have chance, to go for possibly something new that people hasn't developed, and we can just manage to do some probably public surveillance, rescue purpose, or to make it work, do something that can really help human being, not only for entertainment. Alright, so that's all for my part. I think we just proceed. Should we proceed with the Q&A session first, or just after these 4 projects we do one shot?
Maybe we can take a few minutes for question and answers right now.
Alright.
And eventually, at the very end, if we want to go into details for more things.
Okay.
I would suggest that.
How do you compute the distance from the target?
The distance itself, as I mentioned, since the drone has only one camera, so it needs to be moved in order to recognize the distance. So it takes one location, and then it moves up, like probably 1 meter. So the area that is overlapped, the distance will be computed.
Okay.
Yeah, and as for the altitude itself, the drone comes with the ultrasonic sensor, which can detect the altitude of the drone from the ground. But that is only applicable for 6 meter height. Once it's higher than that, it will be based on the pressure sensor. So if it's in a wide area in outdoor, the pressure should be almost the same for different altitude. So that is how they compute.
Yes, but if you move your parrot to triangulate the distance, you need the camera to be calibrated.
Yeah, I mean, since it is industrialized, for entertainment purpose, everything has been calibrated before it is sold to the users.
Yeah, okay. So you use the features and
yeah, I mean,
toolbox and
since it originally this parrot is designed just for entertainment itself, and it already comes with video recording features and text recognition. They go it for games, all this. So it's already designed well. And what we do for our part is that we use rules to set to control the parrot, so that we can develop further based on the rules itself.
okay.
Thank you.
Just about the target provided by PARROT, you show some images with the distance of this target to the camera. Do the PARROT compute several positions in order to compute the distance?
As long as it start moving, then you will compute the distance. Like if you start the parrot and then you put the target in front of it, it won't actually detect. So unless you move it a little bit or you move the parrot a little bit, so once it has two locations, it can compute the stereo estimation.
Thank you.
I don't have any questions right now because we discussed a lot, but maybe just a few comments about the recommendations you provide about the spare parts and so on. Do not worry, we ordered a new PARROT this morning with the new power batteries, so it should arrive very soon. So
Thank you very much.
you can sleep again about this question. And I also wrote down somewhere that you would be interested in further projects.
Yeah.
So you are the really first one interns working on the PARROT to study what's going on with ROS. And we were already sure that you provided new possibilities. So we plan next year to have a swarm of PARROTs, several PARROTs, introduced in our robotics project with master's students. So of course we'll keep in touch about that. So I just wrote it down. Thank you. Other questions? No, later.
Okay, so if you have further questions, we can ask after our colleagues have presented their projects. So thank you very much. I pass the stage to Tiong.
Thank you.
A very good morning to all supervisors. Now I'll talk about the 3D reconstructions with Kinect embedded on TurtleBot 2, which use the RGBD Slam in ROS. And I will talk about what I did for the past few weeks. Basically, I started with launching the commands that I find in the RGBD Slam. I downloaded the RGBD packages, and I also tried some CCNY packages, which is also used for the 3D mapping. However, by just launching the commands, I couldn't understand what it's all about the Kinect, because Kinect itself, later I'll show some pictures about Kinect, it's not on this slide yet. Because Kinect itself is a device whereby we have to really read through about it, and I want to thank also to my supervisors, two supervisors at the back, because during the project discussion last week, they gave me some very important, useful tips, which I have to really study about what Kinect works on, and also the sensors before I can go through into the project itself. So today I will just touch a little bit about what Kinect sensors are, and also the formations of depth image, and also what is my following plan in the near future to complete my project. So this one is the, as you can see from the slide, is the Kinect sensor. In Robotics Lab, I'm given the Xbox 3060 for the Kinect, and there are three cameras, the three holes I say. The one part is the depth sensors, whereby the depth sensors consist of the infrared light, the IR light, the depth image is the CMOS camera, and also this one is the color image CMOS. Actually, the depth sensors is to collect the data for the depth informations, and the color camera is to capture the RGB image, which RGB stands for the red, green, blue. So by combinations of the depth informations and the color image, later on it can produce the depth map. I'll further explain on how things happen. So now I just let all of you have a picture on the what is on the Kinect sensor, and how by using these three, the cameras and also the projector itself, can later on we'll come up with the 3D map. Okay, this is about the formations of how the depth image is being formed. The technique used is the structure light. As you can see from the picture shown is called the speckle pattern, and it is a known pattern of pixels projected onto the object. Let's say we have an image, a picture, when the Kinect is being projected on the image itself. Actually, it is there is the pattern projected on the object which we cannot see. Later, the next slide, I will show you on a very short video, around almost 2 minutes. They use the night vision camera to actually see what Kinect, the eyes of the Kinect. So you will have a clearer, hopefully you have a clearer mindset of how Kinect look at things when So this is a Microsoft Kinect film with a night vision camera to see the speckle vision. You take some time to show on the objects. Only through the night vision camera we can see what the speckle pattern form. Like this one is the speckle pattern, which normally we cannot see with our own eyes. It has to be the device. And this video is not filmed by myself, and I searched from YouTube when I do my research on this. So this is the speckle pattern, exactly same as the picture showing the speckle pattern. So what is the use of this speckle pattern? When the IR sensor project this speckle pattern on the object. This speckle pattern will later on be recorded by the CMOS sensor. So okay. So as you can see, the speckle pattern is exactly what we call the surface shapes are deduced from the distortion of the patterns that are produced on the surface of the object. As you know, an object, there are some distortions, which is the reflections, is the imperfect patterns. So these patterns were detected by the CMOS camera. So with the camera and the projector, the IR projector is using the infrared light. The projector will project the infrared light onto the object and form the speckle pattern. And the camera is used to record the patterns. So with this combination of the camera and also the projector, then the depth can be calculated by the triangulation method. Later I will talk about what is about the triangulation. So as mentioned just now, the pattern is captured by the infrared camera and is correlated against a reference pattern. Actually, a reference pattern is the pattern that is detected by the camera and stored as the memory. So you have a reference pattern. And then when you have the the successive image you capture, because it's impossible Kinect you only capture for one image. So maybe you capture a few images, and the first image will be taken as a reference pattern, and next it will compare with the successive image and calculate the depth. Okay, so this one is the sensor, where just now you got the infrared light projector. You will project the light, and this one is the Seng projected by the invisible infrared light. So using the light coding is also same as the structured light, just the difference of the name you call it. Light coding is also the structured light. And also, okay, this is the depth image. So after the camera collect the speckle pattern, then it will perform the triangulation technique. The triangulation technique, due to the time constraint, I haven't further studied about it. And later on, I think triangulation method is still important for me to know how it use this technique in order to calculate the depth, which we have seen depth image at the end. Okay. In order to construct 3D map, of course we need the Kinect sensor, and it will capture both the depth and color images. So it's not only the depth images, but we still need the color images simultaneously at a frame rate of about 30 frames per second. And through the integrations of depth and color data, it will result in a colored point cloud. And this 3D point cloud can result in the 3D map, because we need the point cloud to form a map, which contains about 300,000 points in every frame. During the past few weeks, I managed to launch the RGBD Slam, and the theory is just that we have the RGB camera to capture the color image, and also we have the depth sensors, the projector and also the camera to have the depth image, and also we have the calculation of the nodes, to actually get the depth data. So the integrations of both data will come out with a point cloud, a 3D point cloud. Okay. By this point cloud. Okay, it's now.
Still good morning. Okay, so basically my research project is, the title is Choreography with Multi-Robots, Fleet of TurtleBots Dance. So it's like making a pattern of how it moves. And basically in my project, instead of the rest of the project, you only control in a single TurtleBot. For my project, I'll be controlling multiple TurtleBots at once. So basically, for my project, I'm choosing to control maybe 4 TurtleBots. And these are the things that I'm looking into now, which is first controlling multiple TurtleBot 2. And next is the choreography design. And lastly, I'll talk about the choreography platform layout. Let us move to here. Yeah. Before this, while I'm moving on with my project, I get to involve myself in presenting during the demonstration on the follower, command, and controlling multiple TurtleBots during the safe wandering in the box there at the other side. So I'm actually applying what I've learned and did some demonstrations for the college students. And, oh sorry, here. Well, the first step that I do to do this project is to control how to control multiple TurtleBots at once. Because at first, when we used to control a TurtleBot from our workstation, we use the command SSH, whereby we can control the TurtleBot from our workstation. But then, since we have to control multiple TurtleBots, SSH command is no longer being used because we can only control one TurtleBot at once. So I tried the codes done by the seniors, and what happens is the TurtleBot can only run in series. That means, let's say I have 4 TurtleBots, A, B, C, D, and TurtleBot B can only run after the commands for the TurtleBot A is finished, since we are using bash script and the command lines in the bash script is executed line by line. So there's a problem for it. So we go and I do some research and findings, and I found the function called terminator, whereby we can just install it and it can be functional in the rows system. And combining the functionality of the terminator and exporting the IP address into different terminals, which I'll be showing later in the next diagram, I'm able to control and give commands to multiple TurtleBots simultaneously. That means it can work with one single command, and it can start simultaneously and end at the same time. Now let us have a look. This is the command that we can give in the normal terminal. When we just type terminator, another new terminal will come out. And in this place, we can split the terminals to how many terminals that we want. In this case, I split it horizontally and also vertically. And I can put in the command separately. As you can see here, I export the IP address to TurtleBot number 53, 55, 56, 57. So with this function of the terminator, I can actually address my commands to different TurtleBots, and I can have a look on what are the progress being done inside. But then there's a problem with this terminator function, because every time we would like to do the choreography, we have to start the terminal to do the terminator, and we have to export manually into each terminal. So my latest finding is, just using the bash script, we can run multiple terminals. It will open on its own, instead of we type the terminator and we have to put in the address. Now using the bash script is just here. It will automatically open a terminal named terminal 1, and then it will split and open up a new terminal. And in this case, it functions just the same as the one that I mentioned earlier, whereby in each terminal, it will run simultaneously. And this is what we should achieve in controlling multiple TurtleBot at once. And next, for the choreography design, basically I tested all the basic movements in both the Bash and Python scripts and drew some comparison between them. And theoretically, the Python script is supposed to be better than the Bash script in terms of giving commands velocity. Because in Python script, most the code is written so that we can have the distance and angle being set by us. Let's say I want the TurtleBot to move 1 meter distance and then rotate 90 degrees. That's it. But for in Bash, we usually express our commands in terms of the twist message, whereby it's being controlled by the time limit. Let's say I want you to move for 10 seconds or 5 seconds. So basically, it's more easier to control the movement of the robot using the Python script. But then, however, I tried a few times using the Python, even though it's supposed to turn, let's say, 180 degrees, but then maybe due to some other factors, the smoothness of the rotation of each TurtleBot is different. I tested yesterday, I give the same command, one is moving 180 degrees, another one is maybe 170 degrees. And the slight difference of the 5 degrees will eventually cause the direction of the next move of the TurtleBot to deviate from its route. So basically that's the problem which I'll be looking forward in the future on how to solve the slight deviation of the rotation. And basically this is the choreography platform layout that I'm planning just for this small little demonstration. As you can see on the floor, I put some orange tapes to make the platform of it, and basically I'm using the dimension of 1.5 meters times 1.5 meters with 4 TurtleBots labeled accordingly. And I will be showing a short, simple choreography. Okay, in this case, I'm just using 2 TurtleBots, and it's going to show how it makes the 90 degrees rotation to make a square. Basically, the rotation most of the times is being affected by the surface. And if yesterday there's a lot of sand on the carpet, and when it moves, it so it's going to affect the movement, and it goes to a different direction. And actually for this demonstration, I'm using the already embedded program, Python program for moving a square. In the program itself, it states that it's going to move for 90 degrees. But then I have to change some of the measurement to 87, then only it moves nicely 90 degrees. Otherwise, it's going to move more than that. Yeah, that's the end. So basically, in the future, I'm going to work more on how to make the movement, the rotation to be more accurate. I'm going to study how to solve the problem, and of course, make a nice choreography for the TurtleBots. And I'll be actually more focusing on the documentation for how the thing works, because making the choreography move is just giving the command. But now, in this case, I'm trying to make it easier to launch the choreography by just launching a file, and then everything will move by its own without having to do another steps at the outside. So I think that's all from me for now, and I welcome any questions.
Thank you.
Yes, I'm not a specialist. I didn't get to the point on the synchronization by using a Bash script.
Alright.
You made a Bash script for Bash scripts, or just one?
Okay, basically when we want to run the choreography, we only type in the terminal bash choreography.sh, and basically in this bash script, it will automatically run other bash script, which means in terminal 1 all the commands that I want to run, and in terminal 2 also the same commands. In each terminal, I will be giving the IP address of each TurtleBot, and inside that, let's say here I'm running the command same start choreography. Here also I'm running the same start choreography, so that it will move simultaneously. Because I'm planning for my choreography, there are two parts. For the first part, you will do the same choreography, and then the second part, each of the TurtleBots will be doing different actions. So in this case, there's no problem in controlling them to move simultaneously. And basically, all these are the sub batch files inside a main batch files where you only run that.
So you have your master script,
So,
the master, the main one,
yeah,
and then call
yes.
for
yes.
every terminal.
Yes, and it's easier for documentation. If you want to make any changes, it will be easier to go into the sub batch files instead of a long one. It's going to be quite messy. Thank you for your question. And more.
Yeah. I've got questions about the Terminator tool, which should the name is funny, but I mean, you mentioned that one of the main drawback is to have to set every time all the 4 terminals in that case, and setting again the ROS master, URI, HTTP, blah 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 in every terminal.
Yes.
What I see is that when you launch Terminator, you've got something mentioned, unable to open config something.
Yeah, it's stated like that, but then it doesn't affect anything to the system at all.
Yeah, of course, but I mean, probably, but I mean, maybe it could worth it to have a look at in the configuration file of this tool. I'm not familiar with it, but maybe you can add some settings when you start Terminator to directly split into 4 simulated simultaneous into 4 terminals, and maybe start automatically one script in every terminal. Maybe of course the tool is not adapted to what you want to achieve at the end, because you already proposed some very good alternative. But maybe it would worth it to spend 1 hour just having a look at this, if the settings can be started automatically in that tool.
Yeah, basically I've tried this. I can start this Terminator from the bash script as well.
Okay.
By initiating how many X terms that I would like to open. But the problem is about how to address the IP address and labeling the terminal. That's the problem with the Terminator. That's why I prefer to use the bash script to split the screen by downloading the application of Spring.
Okay, I get your point. Okay.
But then I'll spend some time by looking at it. Maybe I'll find something more.
Yeah, you should already dig around. I have another question about what you mentioned about the drift you've got in the rotation mainly.
Yes.
in your choreography. You said it. Do you use the gyro?
Yes.
Inside?
Yes.
Okay, already.
It's already inside.
And even with the gyro, you still have this big drift, because the drift seems very important.
Yeah, by right, I thought it should just function as it is, but then when yesterday I'm doing the testing on it, at first, and I'm not sure whether, I'm still looking at the battery percentage, because yesterday when the battery is full, it moves very smoothly, but then when the battery is about half, the rotation speed started to decrease, and then it will affect the choreography.
Yeah, of course,
So
the battery level voltage can affect a lot.
The
way the actuators are, okay.
So yesterday when I'm trying on 2 different TurtleBots, one with fully charged, another in 50%, with the same command, they are doing different things.
Okay.
So I'll study more on how to control it with
and
more high
about that, I would suggest you to get into the best conditions for your experiment.
Yeah.
If the battery levels needs to be the same on the 4 TurtleBot, let's state this is a requirement.
Alright.
Because I guess you will have a lot of problems related to that. It's not because you're not doing good work, it's intrinsic to the robots themselves.
Anyway,
and if we need to clean the floor every time before demo, let's do it. I mean, we always We can do it, of course. But I mean, yeah, we already know this kind of problems. We have a lot of problems last semester, and yeah, do not, I would say, lose some time on this in order to try to make it robust, because this will be difficult.
Yeah.
Okay. I have no other questions. Thank you for the maybe just one remark. Of course, here we all know the TurtleBot by heart. We've worked a lot on that. But for other colleagues or other public, maybe just put one slide on the TurtleBot itself. Can be also useful for the PARROT. Just one slide to explain roughly, less than 1 minute, what is your robot you're working on. For used people, it's not a problem, but for guys out of the lab, that could be important.
Thanks for this discussion.
Thank you.
Thank you. Now I'll have my friend Kelvin Ting to present about his project.
Now it's my turn. So what I'm going to present is about 3D reconstruction using LIDAR on PARROT. So what I'm going to do in my presentation is firstly, I will, for the benefit of the supervisors in UTP or for other people who doesn't understand what is LIDAR, I'll briefly explain what is LIDAR and how does it do 3D reconstruction. And then secondly, before I move into encoding and decoding of the sensor itself, I will briefly explain the kind of the approaches that I've done and then the problems that I have faced that eventually leads me to the need to understand the sensor itself before moving further on 3D reconstruction. And in the end, I'm going to talk about the aim and the plan in the near future. So the first one would be 3D reconstruction. Mainly it is to produce accurate digital elevation models of objects or buildings for the benefits of industrials if they want to reconstruct a building or other purposes. And then LIDAR actually stands for Light Detection and Ranging Systems. So the basic concept is it positions a footprint of a laser on an object to detect the distance or to detect where the object is. So the main method of LIDAR calculating the distance is using the travel time, because we all know the speed of light, and then the infrared light that projected by LIDAR would be calculated, and then that is how distance can be determined in the end of the day. So to obtain accurate coordinates of object besides the distance, we need other information such as laser scan angle, laser position from GPS, and laser orientation. These are different from the way you set it up and different from sensor to sensor. So the sensor that I'm working on is URG04LX UG01. So this is the picture of it. And just simple specification is its detection area is 240 degrees and the detection distance is 0.02 meter to 4 meter, and it is mostly suitable for indoors. So if you use it outdoors, so the specifications might not be that correct in that sense. And it is very suitable to be mounted on a robot because of its lightness. It is the weight is very light, and then it is considerably cheap and accurate in the sensor field. So before I move into data encoding and decoding, what I've tried is I tried a tutorial on a ROS. So I managed to get a scan of the environment around me. I didn't have the picture, but I managed to get a scan, and then I managed to record it in the back, and then I managed to play it back. But to make it as a map, we need some other packages, such as when I found, without mounting it on a robot at first, because that is the end aim of my project, I need to map it using handheld mapping first. That is what I decided. So through online researching, only Hector mapping, or the most popular mapping, is using Hector mapping without odometry that doesn't require a robot. So I tried Hector mapping, but in the end it fails in the sense that I managed to open it and visualize it. It can run in ARVIS, but the map couldn't be produced. The map produced is something like overlapping points that doesn't really record the real map of the sense. It just records, if you move the sensor a bit, then the map will be distorted wholly. You cannot actually have an accurate map. So I decided I need to understand how it decodes and encodes data first, and then how it grabs a set of data, and then to be able to analyze it and manipulate it before I move on forward to understand why the set of data didn't work together. Maybe the packages is wrong, or the frame is wrong, or it doesn't correlate with each other. So actually it has a very simple data encoding and decoding. It just involves a few steps. And the first one is just converting from decimal to binary, and binary to hexadecimal, and adding 30 hexadecimals. And in the end, it converts to ASCII equivalent, which uses the ASCII table. And then the bottom 3 and 4 is wrong, so just disregard it. So in the end, in the computer, it will decode it back. So the purpose of this encoding is to minimize the time transmission of the sensor and the host. So just a brief video explaining what is the aim of this project. The nearest aim is to do it without photometry. That is what is explained or what is shown by the person here. He just holds a sensor, and then he can make a map with regard to the position of the map and the walls and the sensors. So this is what I'm going to try to achieve, and in the end we will get a map that is the whole. In this aim is to make this room, for example. So in addition to mapping, the task that I've been given is to mount it vertically. I've been thinking about the benefits of mounting it vertically because in the current time, many robots mount it horizontally, and they have a tilt angle to scan the map and whatsoever. But the only thing that I can think of, by mounting it vertically, perhaps we don't need a tilt angle, because when you mount it the way you want it, and it has a 240 degrees scan angle, you can just move the robot, and you don't need it to be tilted. You just need to move a robot and rotate it at a specific point, and you can get the map. So perhaps it will be less complicated to include the tilt angle in the programming process. So in the near future, what I'm going to do is I'm going to learn how to grab a set of data and analyze it and manipulate it. Provided now I know the codes, and if I got the raw data, then I will be able to understand what is inside, and to execute some commands for the sensor directly, such as some QT sensors that stands for stopping the sensor to record data, and some other sensors, other commands to input commands to sensors. So basically that ends my presentation, and I welcome any questions.
Thank you.
So what will be, if your goal is to reconstruct such a scene, for instance, do you have any idea of what you will be doing? What kind of techniques you will use?
The thing that I have known up to now is to use some packages to record many sets of LaserScan data, and then to compile it using ROS packages, and then in the end that produce a map. For handheld, you don't need to consider odometry or frame, but when you mount it on a robot, you need many complications such as TF transform and the frame that you're going to use, and those things that will be studied later.
You plan to use the odometry?
Yes, in the end of my project, yes. But before using odometry, I plan to make it to map without odometry first, to make sure that I know how it maps before considering odometry.
Have you been able to use the LIDAR to capture 3D and so on and so on?
I only managed to capture a set of measurement, like the distance, but for a consecutive measurement that I haven't succeeded. The only thing that I get is distorted maps that overlaps on each other. the set of data get overlap with each other. So now I'm trying to solve that problem to understand why is it that.
Thank you.
Yeah, I've got a lot of remarks about, and I guess that I understand why David asks the questions, because you study the sensor and you already have results. I mean, we've seen together that you have some slit of measurements, but you didn't show them. Why? I mean, you've got a slide where you present your sensor and you talk a lot about it. You say, I already tried this, and now I have to handle further steps by adding, but you don't show examples of what you have. If someone in the audience have never seen a Hokuyo LiDAR, we don't get the point. I mean, you should put some schematic to show that your sensor is sweeping the area in front of it, measuring the time of flight, and recovers the distance and store it with an angular step. If you didn't describe it, I guess. So that's why the rest of your talk is very difficult to follow for someone who is not involved in the project. You see my point? You talk about RVs, mapping, a lot of things like that. You have examples to show things in order to explain that you already managed to get data. Your sensor is working. You made it work. But show some results. Even at the beginning, if you don't really manage to do hectare mapping on quite advanced use of the sensor. And this is very frustrating not to see that. See my point? And on your opinion, I mean, you showed some example of the coding of data. You've got one slide on that. You go at a very, very low level, but what's the point?
Because actually, that is the question that I'm wondering myself as well. Because when I realized that there is a problem with the map that I'm trying to do, I didn't know where to approach. So I figured out I have to understand the sensor at first. So if, let's say, if in the future, if I want to go into a text file that contains this sort of data, then maybe in the end I would understand these are the range of measurements and these are not. So maybe that, I think that's my first step of understanding the code.
I mean, it's a very good approach to be curious of what's going on backstage. But I mean, I guess that this level is very, very low. And you don't, I mean, when you're handling ROS messages, LaserScan messages coming from your sensor, between you and me, you really don't care if it's binary or hexa coding on the frame where you put 30 at the beginning and adding some things later. This is quite close to hardware, electronics. And this is not the topic. Here in ROS, you probably know that you've got the LaserScan message where you've got the set, a vector, where each distance is coded, is recorded as a value, floating value. Did you study that?
That part I only touched about the back. I haven't go inside that.
I mean, I guess we didn't understand each other when we suggested you to dig into the very basics of the sensor. Not the electronics level, because you're gonna be lost in that part. But a little bit higher in ROS, how you handle your measurement in ROS and do simple things before going to mapping, because mapping is handling a set, as you mentioned, of different laser scan. This is future work. At the beginning, image correctly and do schematics to handle correctly your sensor. And you shouldn't go too low in the details on the SAAD sensor, because it can be very complicated. and probably useless for the rest of the project. This is a suggestion on that. Okay. For me, it's okay. Other questions? No? Okay. Thank you.
Thank you very much.